Air flows steadily and isothermally at 27 Celsius along a straight horizontal pipe of constant cross-sectional area 100 centimeters squared. At point A, the pressure is 3 bar and the mean velocity is 160 meters per second. Point B, the pressure is 2 bar. Find the velocity at point B. So, and part B, calculate the heat transfer per kilo of air between the 2 points. So I suggest we start by sketching this flow, noting what information we already have, and thinking about what principles we need in order to solve the question. So the diagram looks like this. So constant area duct. Our control volume is this dotted line from location A to location B. Here the pressure PA is equal to 3 bar. That falls to pressure at B is equal to 2 bar. The mean velocity at A is also, so we'll call that C bar. The bar is for average at A is equal to 160 meters per second. We need to calculate now the velocity at point B. Now the area is constant. 100 square centimeters. However, because the pressure changes, the density is not constant. So we know the working fluid is air, so we're going to treat it as an ideal gas. And there are two principles we can apply in order to solve this problem. The first is the ideal gas equation, the second is mass continuity. So all the mass flowing at point A has to, by steady state, flow through point B, or the same amount of mass has to flow through both places. So the temperature at A is also 300 Kelvin. And the statement of mass continuity is that the mass flow rate is equal to rho A C at any, or the average value of C at any location. Okay. And so at point A and point B, both rho are different and C will be are different, but the value of A and m dot are the same. So part A, we need to find out what the density of air is. We don't have enough information to find that at point B yet, because we don't know what the temperature is, but at point A we know both the temperature and pressure, and we can use the ideal gas equation. So rho A is equal to pressure A over R T A. So this is the specific gas constant for air, and this is an expression of the ideal gas equation, or a rearrangement of the ideal gas equation. And the value of R for air, I suggest you learn, is 287. And the units of that would be joules per kilogram per Kelvin times the temperature at TA, 300 Kelvin. Kilograms per meter cubed. Okay. In fact, we do know what the temperature at B is. We're told that it's an isothermal process. So TB is also equal to 300 Kelvin, or 27 Celsius. So given that we know that, we can say that the density at point B is equal to PB over R is the same, TB. We know, in fact, both of these quantities. So this is now our expression for the velocity at c, or the flow speed at c. We can cancel the area because it's constant. And so it's just changes due to the change in density. And the value we get is 240 meters per second. Part B, calculate the heat transfer per kilo of air between the 2 points. In order to calculate this, we can apply the steady flow energy equation. So it tells us the relationship between changes in, say, heat input and enthalpy. So if we write it in per kilo, so that would be Q minus the shaft work into control volume, which is 0, is equal to HB, so that's enthalpy flowing out minus enthalpy going in, HB minus HA, plus half Now, since we're treating air as an ideal gas, the enthalpy is only, or as a semi-perfect gas even, the enthalpy is only a function of temperature. So since the enthalpy is a function of temperature, and since TB equals TA, therefore HB equals HA. So these terms, these specific enthalpy values are constant, or are the same, so the heat input is only related to the change in velocity. And we'll assume that the change in elevation is 0. So heat input per kilo of flow is equal to half CB squared, and we could put the value in there straight away since we've calculated already, which was 240 meters per second unit squared minus 160 meters per second squared. If we put the numbers in, that gives us 16,000 joules, or 16 kilojoules per kilogram, since we wrote the equation in terms of kilos. So that's adequate. That's the answer to that question. So just by being clearer about the principles we're applying and writing things clearly, we shouldn't make any